If you suffer from seasonal allergies, like I do, then you know that spring means airborne pollen, and that pollen means sneezing. Now, let's say you work in R&D at a pharmaceutical company, and that you've developed a new medicine that can help reduce sneezing caused by pollen. If you had to build a Bayesian model to help you predict how effective your new medicine is in reducing sneezing caused by pollen, how would you build it?
Hmm.
Well, let's find out. Welcome to Dago.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. The bulk of the code for today's tutorial comes from the tutorial section in the Turing.jl documentation. I've taken their code and modified it for the purposes of this tutorial. There are a lot of great tutorials in the Turing.jl documentation, so be sure to check them out if you're hungry for more tutorials. I provided a link to the source material in the description below. In the interest of time, I've prepared some code and an interactive Pluto notebook in advance. You can find a copy of my code and a copy of this Pluto notebook in my GitHub repository. There's a link to my files in the description below as well. If you want to follow along, you can save a copy of these files in a tutorial folder on your computer. After you save the files, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square brackets. Activate the tutorial directory. Add the following packages: CSV, data frames, stats plots, and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. Okay, now that we have our packages loaded, let's download some data. As a motivating example, to help us learn about Bayesian Poisson regression, we're going to use a contrived dataset that I've prepared using random data, based on the methodology presented in the Turing.jl tutorial documentation. I'm executing the code to download the data off the internet and into a data frame. If you're typing this code in manually, you can find a copy of this URL in the description of this video. Click on the Julia logo icon and click on the table icon next to the df variable to see the data. This dataset contains 3 columns labeled pollen, meds, and count. Both the pollen column and the meds column contain booleans. So a 0 in the pollen column means that there was no pollen in the air, and a 1 in the pollen column means that there was pollen in the air. Likewise, a 0 in the meds column means that the individual did not take allergy medication, and a 1 means that the individual did take allergy medication. The count column records the number of sneezes that the individual experienced on that day. If you click on the count header a few times, you can see that the number of sneezes per day ranges from 0 to 27. Each row of the dataset is a record of a single day, and the dataset contains 400 rows for 400 days. Using this data, we're going to create a Bayesian model that we can use to predict the number of sneezes per day for this individual based on whether or not pollen was in the air that day and on whether or not the individual took allergy medication that day. But before we can do that, we need to do a little data wrangling to split our data into 4 subsets to capture the following groups: no pollen, no meds; no pollen, meds; pollen, no meds; and pollen, meds. Okay, now that we have our data split up, let's visualize the data so we can see what we're working with. I'm executing the code to generate 4 separate plots, and then combine them all into a single plot. These 4 histograms are arranged in the same order as the blank grid that we saw earlier. So looking at the rows, the top row shows the distributions of the number of sneezes on days when there was no pollen in the air. And the bottom row shows the distributions of the number of sneezes on days when there was pollen in the air. Now looking at the columns, the left column shows the distributions of the number of sneezes on days when the individual did not take allergy medication. And the right column shows the distributions of the number of sneezes on days when the individual did take allergy medication. So going from lowest to highest, the individual experienced the lowest number of sneezes on days when there was no pollen in the air and when they took allergy medication, followed by days when there was pollen in the air and when they took allergy medication. Next were the days when there was no pollen in the air and when they did not take allergy medication, followed by days when there was pollen in the air and when they did not take allergy medication. Now your job is to create a Bayesian model that can generate these observations, so you can use it to predict the number of sneezes per day based on these scenarios. Our going-in hypothesis is that the number of sneezes per day is caused by pollen in the air and the use of allergy medication. Using this hypothesis, let's split our dataset into features and labels so we can use them for further analysis. The features are contained in the columns of Booleans for pollen and meds. The labels are contained in the column for the number of sneezes per day. Okay, we now have everything that we need in order to build our Bayesian model. But before we do, let's get a quick lesson on some of the concepts that we need to build today's model, including a crash course on the Poisson distribution. For today's distribution, I wanted to use the Poisson. In the interest of time, I've prepared this Pluto notebook in advance. You can find a copy of this notebook in my GitHub repository. There's a link to my files in the description below. In this section, we're going to cover the Poisson distribution, multiple linear regression, and log transformations. We're going to use all of these concepts to build our Bayesian model. The Poisson distribution is named after the French mathematician and physicist Siméon Denis Poisson. The Poisson distribution is an example of a discrete probability distribution, like the binomial distribution. The Poisson distribution expresses the probability of a given number of events occurring in a fixed interval of time or space. For example, we're going to use the Poisson distribution to express the number of sneezes per day. The function for the Poisson distribution takes a single parameter, lambda, which is the average rate of occurrences. The parameter lambda must be a number equal to or greater than 0. When lambda equals 1, the probabilities are clustered near 0 and 1, but tails off quickly, moving to the right. As you increase the value of lambda, the probability distribution begins to resemble a normal distribution, except using discrete numbers of events. Because of the nature of this probability distribution, the Poisson distribution is especially useful when the events are rare, like 1, 2, or 3 events per unit of time or space. So that's the Poisson distribution. The next concept we need to review is multiple linear regression. We've already covered linear regression, and you're already familiar with the equation for a straight line, which is y equals mx plus b, where m is the slope and b is the y-intercept. That equation for a line is a special case of a more generalized linear equation, which is what you're seeing on the screen now. In the generalized form of a linear equation, there's still only one y-intercept, which is noted here as beta sub 0. Beta sub 1 is what we've been calling m for the slope of the line. In the past, we've only used one value for the slope of the line. But you can, in fact, use as many values of the slope as you want, which is noted here as beta sub 1, beta sub 2, and so on. These slope values are known by various names, like coefficients, parameters, and weights. This can be useful when there are more than one explanatory variables in your dataset. For example, in today's dataset, we're using pollen and meds as variables to explain the number of sneezes, which is the dependent variable. So the takeaway here is that you can define a line by using multiple coefficients. The final concept we're going to cover today is something called a log transformation. Log transformation is a term given to a collection of methods for transforming curves into straight lines and transforming straight lines into curves. This can be useful if your data is skewed and you want to stretch it out to get a better understanding of your data. Or you may want to bend a straight line into a curve to use it with other functions that expect the input to be nonlinear. That's what we're going to do today. We're going to take a straight line and bend it so we can use it with a Poisson distribution function. In this interactive model, there are 3 sliders. The first slider controls the value of the y-intercept. The second slider controls the value of the first slope coefficient. And the third slider controls the value of the second slope coefficient. The top plot is a plot for a straight line, and the bottom plot is the transformed version of that line. Now, when all of the sliders are set to 0, both plots display a horizontal line. The only difference is where the lines cross the y-axis. In the top plot, the horizontal line crosses the y-axis at 0. In the bottom plot, the horizontal line crosses the y-axis at 1. If you change the value of the intercept, the lines simply move up or down. Changing the intercept doesn't change the shape. If you increase the value of coefficient 1, notice what happens to the plots. So the slope of the line in the top plot increases slightly, but the straight line in the bottom plot transformed into a curve. The curve still crosses the y-axis at 1, but the y values increase dramatically for the positive values of x. And the y values approach 0 for the negative values of x. The y values in the bottom plot will always be positive, which is useful for us since the function for the Poisson distribution only takes numbers equal to or greater than 0. Now notice what happens when you increase the value of coefficient 2. Increasing the second coefficient also increases the slope of the line in the top plot slightly. But again, it has a dramatic effect in the bottom plots. Now try changing the intercept value again. Again, changing the value of the intercept simply moves the line or curve up or down. It doesn't change the shape. By tuning the values of these parameters, you can find the settings that work best for your datasets. Pretty cool, right? Okay, we now have everything that we need in order to build our Bayesian model. For today's model, we have prior beliefs for 3 input parameters, the intercept, and 2 coefficients for explanatory variables, which are pollen and meds. Our prior belief is that these values are normally distributed with a mean of 0 and a standard deviation of 1. For the likelihood, we're going to apply the concepts that we just learned to model our belief that the number of sneezes is distributed as a Poisson distribution. Okay, let's talk about that likelihood section. So inside of that for loop, the equation for the line is an example of multiple linear regression that we just learned about. Coefficient 1 is pollen, and coefficient 2 is meds. The equation for a line is then transformed by using the exp function from Julia Bayes to bend the line and to ensure that the values are always positive. That equation for the transformed line is then used as the lambda parameter value for the Poisson distribution. Again, the lambda parameter is the average rate of occurrences for an event in a given time or space. Now that we've defined our model, the inference step is the same as we've seen in other tutorials. We're using the NUT sampler again and drawing 1000 samples. In the summary statistics table, you can see the mean values for the parameters. Let's take a look at the mean values for pollen and meds. The value for pollen is a positive number, and the value for meds is a negative number, which is about twice the magnitude of the pollen value. So based on these values, we can conclude that our posterior belief is that the presence of pollen will increase the number of sneezes per day, and that by taking allergy medication, the individual can expect to dramatically reduce the number of sneezes per day. Now let's visualize this chain to get a better understanding of the probability distributions. It looks like our model has converged on a set of probability distributions with fairly small standard deviations, so there's only a small range of possible values. This suggests that our Bayesian model should fit our dataset pretty well. Let's try using our model to make some predictions to see how good our model actually is. As we've done in the past, you can make predictions in the Turing.jl package by using the predict function. For the new x values, I'm using a matrix which shows the 4 scenarios: no pollen, no meds, no pollen, meds, pollen, no meds, and pollen, meds. The missing values are the number of sneezes per day for each scenario, so we need a vector of missing values here. And then we can use these new inputs with our model, and use the model with the predict function. In the summary statistics table, you can see the mean values for the average number of sneezes per day for each scenario. Scenario 1 is no pollen, no meds. Scenario 2 is no pollen, meds, which you can see has the lowest average value. Scenario 3 is pollen, no meds, which you can see has the highest average value. And Scenario 4 is pollen, meds, which is higher than Scenario 2, but lower than Scenario 1. Recall that Turing predictions are not values, but rather probability distributions. So let's go through the details behind these predictions. Click on the Julia logo icon and click on the table icon for the predictions variable. So Turing went through each row of the chain and predicted the number of sneezes per day for each of the 4 scenarios by using the parameter values in that row of the chain. In total, there are 1,000 rows in this prediction table for the 1,000 samples in our chain. We can visualize these predictions by using the plot function. There are 4 sets of diagnostic plots, one for each scenario. Just for comparison, let's recycle our earlier plotting code and place the histograms for the original dataset next to these histograms for our predictions. You can copy and paste the code from above, rename the plot names, and replace the original plotting data with the data from the predictions chain. I also modify the code for the final layout so that it's a little easier to look at. The histograms on the left-hand side are from the original datasets. The original data had 100 observations for each scenario, so the frequencies add up to 100 in each of the histograms. The histograms on the right-hand side are from the predictions. The predictions have 1,000 samples for each scenario, which is why the scales are different and why the bars are thinner. The frequencies for the predictions histograms add up to 1,000. So the predictions from our model are pretty close to the original dataset, with the added benefit of having nice Poisson distributions. Just for the record, here are the lambda values that I used when using the Poisson distribution to generate the original dataset. For scenario 1, or no pollen, no meds, I used a lambda value of 9. For scenario 2, or no pollen, meds, I used a lambda value of 1. For scenario 3, or pollen, no meds, I used a lambda value of 16. And for scenario 4, or pollen, meds, I used a lambda value of 4. So Turing pretty much nailed the predictions. Now that you know how to use it, you can add Bayesian Poisson regression to your ever-expanding toolkit of knowledge. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!